Is this your tripod or is it ours?
No, it's Jerry.
Jerry's?
Jerry,
Okay.
he's the one.
Okay.
I don't know who it.
I'll keep it back here for him then.
Okay, all right, thank you.
I'm ready. Are you ready?
Yeah, we ready?
You ready?
Yeah.
Okay.
It's dark.
All right. Brianna,
Yeah.
40% stage lights, please. Is this live? Yeah. Okay.
Yeah, that would help.
Hello, and welcome to the 2015 Bullitt Lecture in Astronomy. This is the 15th lecture, so it shows some staying power. It's a bit of a landmark. I don't know what the weddings have these days when you have landmarks. I know 25 is silver and 50 is gold. I don't know what 15 is, but it's probably something pretty good. So I appreciate all of you coming. I especially would like to thank our Dean, Dr. Kimberly Leonard, and is our Vice President for Research, William Pierce here? Maybe here. And Bob Buchanan, our Associate Dean. And there are members of our department. A big production like this always takes a cast of many people, many of whom work behind the scenes. They should not work in anonymity. I would like particularly to thank the people who helped with publicity and putting up posters. Are there any members of Mortarboard here? Stand up, yes. Mortarboard helped to put up posters on campus and in town. And also members of the Society of Physics Students. Are any members of SPS here? Yes? Okay. SPS also helped. And also in the community, members of the Louisville Astronomical Society, LAS. Are any LAS members here? Okay, please show yourselves. They help as well. Actually, I'm a member of LAS too. I need to pay my dues. Yeah. So these three organizations, Mortarboard, Society of Physics Students, and Louisville Astronomical Society, help us with publicity, word of mouth, and they come in force, and we appreciate their help to get the word out to you, the general public, to help our mission as a metropolitan research university, which is education. Education for our students and education for the community and service to the community. And one of those is to find out about how we spend our tax dollars. But this lecture is funded by the generosity of the William Marshall Bullitt Fund. William Marshall Bullitt was the Solicitor General of the United States under President Taft. And he was a lawyer here in Louisville. He studied law. He was also an ambassador, if I remember correctly. No?
Get there.
He was a graduate of the University of Louisville Law School. And so this fund has been set up to commemorate him because he loved astronomy. He loved mathematics. He was a lawyer. And so this combines actually astronomy and mathematical science. And so we celebrate his interest. And so part of the package that comes with this lecture is we also make presentations for 2 scholarships. And here to present scholarships is Mr. Lowry Watkins Jr., who's the grandson of William Marshall Bullitt. So our first award winner is Blaine Cinta, who is our Bullitt Scholar in astronomy. Blaine, could you please come down? Blaine is a senior in physics and astronomy, and he's been diligently working. He's done some research on distant galaxies, and he also, in his spare time, works at Apple, which working for a computer company actually is very handy for physics and astronomy majors. So he has demonstrated not only an interest in astronomy, but lots of hard work. And we would like to congratulate Blaine Cinta for being this year's Bullitt Lecturer, or Bullitt Scholar in Astronomy. You can come down and make a nice picture for posterity and austerity.
Sorry.
Okay. All right. Our next winner is Jeremy Hornbeck for the best paper in astronomy. Jeremy is a PhD student working with one of the members of our faculty, and he's also yes. Okay. We've drunk many coffees together. We've supported the Heine Brothers retirement fund. So he's also working with Dr. Carol Rady of NASA Goddard Space Flight Center, and Jeremy wrote a paper on it, and I'll let you give the title and tell us a little bit about it.
Well, the title is kind of confusing, but it's a paper about Geomorrhagi, a star that is forming planets as we speak, and it's a great tale about how planets form around young solar systems.
That's going to be probably the subject of one of our future Bullitt lectures. So what Jeremy did was he assembled data from the Hubble Space Telescope. He also has looked at data from ground-based sub-millimeter telescopes, done some modeling to work out exactly how baby solar systems form. And so thank you very much, Jeremy, for your contribution to academic learning. So astronomy at the University of Louisville is progressing forward, and we have students doing great things. We also, as part of our mission, we want to contribute to public education. So we have this lecture series. We invite speakers from elsewhere to give a talk. This year's Bullitt Lecturer in Astronomy is Hal Weaver from Johns Hopkins University Applied Physics Lab. So many of you have heard of Johns Hopkins University. The Applied Physics Lab is a laboratory which does a lot of research. Much of it is government sponsored. Among other things, and he can tell you perhaps more, they ran things like the Mercury Messenger mission, which is the first orbiter to Mercury, and also they were the the control center for the Pluto New Horizons probe, which was the first probe to Pluto, and actually the first of a class of missions which was headed by a principal investigator rather than NASA itself to the outer planets. And it's a long way out there, folks, so it's pretty hard. He did his bachelor's degree at our ACC collaborator sister institution, Duke University, and then he did his PhD at Johns Hopkins University. He sandwiched in a postdoc at NASA Goddard Research Flight Center, GSFC, NASA Goddard Space Flight Center. And then he went back to Johns Hopkins. He was on the main campus for a while, and he went out to the Applied Physics Lab. He has studied comets for 30 years, so he knows a few things about comets. He's going to talk about comets in the Rosetta mission. And he also is the project scientist for the Pluto New Horizons probe. So I present to you Dr. Hal Weaver.
Hey, I'm supposed to be mic'd up. But I can tell. Can you
Yep,
hear
you're
me
all right.
now? Hello?
You're good.
Am I good?
Yeah, you're all right.
Okay, thanks a lot, Jerry. Yeah, it's
he's
been
not.
an exciting summer for us. We work in space science, especially for... Whoa.
Maybe you should put
Oh,
the
got it. This fell down.
That's the difference.
There we go. Okay. It doesn't have its little...
Oh, it's just a little tiny one. Go ahead and put it on.
Okay, gotcha.
That's better.
Okay.
Probably got caught on the chair.
Let's see. There we go. Sorry about that. Okay, now, hopefully that's better. Okay, so I'm going to be talking about some brand new science, the exploration of what we call the solar system's third zone. First of all, I'll explain what I mean by that, but I'll be talking about two missions, and that's a big task because I could easily spend a couple of hours talking about just the New Horizons mission itself and the exciting results we got this summer. But at the same time, this year also is, we're in the middle of a mission called Rosetta, the first spacecraft mission to orbit and land on a comet nucleus. And so that's been very exciting. I've got both of these things going on at the same time, and I'm going to try and run through some of the exciting results from both of them. So, we'll see how that goes. But in the upper left over here, you can see an artist's rendition of the New Horizons spacecraft as it's approaching. This is the artist's rendition of Pluto and Charon. This is the real Pluto and Charon, as we now have been revealed by New Horizons. This is one of the iconic views in real color, natural color that you would see with your eye, Pluto and Charon. And so I'm going to spend most of my time talking about the results from the New Horizons mission. But Rosetta, like I said, is out there as well. And really ambitious mission, as you'll hear about, where they actually took a package and landed it on the surface of a comet. So it turns out that both of the targets of those two different missions ultimately came from the same place, the so-called Kuiper Belt. This is the third zone of the solar system. Now I'm showing you this figure over to the right. These are the actual positions as of July, middle of July of this year, of every known object in the solar system. Okay? The Earth is way in here in the very center, hardly raised here. That's a part of the terrestrial planet zone, okay, the first zone in the solar system. And those are the objects in the first zone are comprised of relatively small rocky objects. You've got Mercury, Venus, Earth, and Mars. But you step out a little bit farther, and you get into the second zone. This is the realm of the giant planets: Jupiter, Saturn, Uranus, and Neptune. These are Jupiter, of course, is the big gorilla in the solar system, more than 320 times as massive as the Earth. All of those giant planets have huge gaseous envelopes made of molecular hydrogen. You see this is the orbit of Jupiter, which is 5 astronomical units from the sun. We measured distances in the solar system with a unit called the astronomical unit, which is the average Earth-Sun distance, 93 million miles. It's just instead of talking about inches or feet, we use AUs. So that's 5 AU. You step out a little bit further and get to Saturn, Uranus, Neptune. Now, in 1930, Pluto was discovered by Clyde Tombaugh, who is an American astronomer working at the Lowell Observatory in Flagstaff, Arizona. And he was actually looking for a big planet out there that was perturbing the orbit of Neptune. But it turns out he found Pluto instead, and it stood out like a sore thumb. He had no idea what this object could be, because it had this incredibly weird orbit. You see here, it actually passes inside of Neptune's orbit. Neptune is out at 30 AU, and Pluto actually gets to within 29 AU, and it did that in 1989. That's the so-called perihelion of Pluto, the time when it reached the closest point to the sun. But it goes all the way out to 48 AU in this elliptical orbit. So instead of being nearly circular like the Earth's orbit around the sun, we're always almost exactly 1 AU from the sun. This goes over a very large distance. And not only that, you look at the side-on view, because that view that we just now saw was looking from above the solar system and down on the projection onto the plane, the so-called ecliptic plane that contains the Earth, the Sun, and Jupiter. Now, if you look from the side, look at Pluto's orbit. It's tilted by 17 degrees to that plane, okay? And in the 1990s, astronomers discovered the next object that was in that same family, in that same region of the solar system, and then it just took off like crazy. And now we have over 1,000 objects that have been discovered in that region of the solar system, and they're denoted by these little white dots here. The Kuiper Belt. This is the Kuiper Belt, the third zone in the solar system. It's almost like a donut-shaped region around the sun, extends from about Neptune's distance all the way out to about, that's 40 AU, 30 AU out to about 50 AU, okay? And it's filled with all of these objects. And Pluto, we now know that there are 3 different families of objects in the Kuiper Belt. Pluto is what's called a resonant object. It's in a class of objects that are in a 3-to-2 resonance, orbital resonance with Neptune. Okay, so when Neptune goes around 3 times around the sun, Pluto dances around twice. And even though it passes inside Neptune's orbit, because of this resonance, it never actually gets very close to Neptune. So it's always protected in that little zone. And there's a whole bunch of objects that are out at that in that same resonance, and they're called Plutinos. Okay, Pluto is the largest of those. But another class of objects is what we call the scattered disk, and those are the ones that are that aren't in the plane here. They have even higher inclinations than Pluto, higher tilts in their orbits around the sun, and those, it turns out, from that population comes the short period comets. Okay. Like the one that the Rosetta mission is going around, we think ultimately came from the Kuiper Belt originally. And those are denoted by the caret symbols. Those are all comets, things that are little caret symbols, okay? That's one category of comet. There is another category of comets that come from a Oort cloud, like Comet Hale-Bopp, has this 90-degree inclination angle. But tonight we're just going to be focused on the two different types of Kuiper Belt objects. The ones that are like Pluto, the resonant object that will focus on Pluto, that is the target of the New Horizons mission, and also Rosetta went after Comet Churyumov-Gerasimenko. 67P is the short version of that one. And the discovery that there were these 3 different families of Kuiper Belt objects actually has revolutionized our view of the solar system and our understanding of the formation and evolution of the solar system. Because in order to explain the existence of this Kuiper Belt, it turns out that you really need to have a huge amount of radial migration of the giant planets in the solar system. So we were all taught, at least I was, maybe now we're starting to teach differently, but that all the planets, the giant planets, Jupiter, Saturn, Uranus, and Neptune, they were always where they are now. Okay, and it turns out that that's probably almost certainly not the case. We think that Jupiter actually, during the early stages of the solar system's formation, actually came to within almost Mars's orbit and then went back out again. And because of its giant, because of its strong gravity, it's actually, it perturbs everything else, all the other giant planets. And they go through this really chaotic excursions orbitally. And in fact, we think that Neptune and Uranus actually flipped spots. So Neptune was actually, during the formation of the solar system, the original formation 4.6 billion years ago, was actually closer to the sun than Neptune is. But now they flipped. Okay? And now we've reached a stable configuration of the current solar system. But that's not the way it was. And the new view that there was this huge amount of radial migration that pushed the Kuiper Belt objects into to where they live now. That all was a result of the discovery of the Kuiper Belt. By the way, Kuiper is named, the Kuiper Belt is named after Dutch-American astronomer Gerard Kuiper, who used to work at the University of Arizona. Okay, so now let me go on and talk specifically about the very first mission to the Kuiper Belt. Okay, it's actually has, we've had these other missions, the Voyagers and the Pioneers have gone out beyond, into the Kuiper Belt region, but they never flew by anything in the Kuiper Belt. The New Horizons mission is doing the initial reconnaissance in situ of Kuiper Belt objects. And the king of the Kuiper Belt is Pluto. It's the brightest and the largest. I mean, some of you may have heard back in 2005, the discovery of Eris, that Eris was bigger. Well, it's not true. We now know from the New Horizons mission that Pluto remains the king of the Kuiper Belt. And so our mission, though, was approved in 2002. We started the mission. We launched in January of 2006. The New Horizons spacecraft was the fastest spacecraft ever to leave the Earth. Okay, it was amazing. We saw it taking off at 2 p.m. in the afternoon. In fact, let me just go forward and tell you first of all that in order to send the spacecraft to Pluto, Pluto is way out there, 3 billion miles from the Earth. Okay. In order to get out there, we had to find the largest rocket available to us, which was the Atlas 551. This huge thing, 200 feet tall, with this 5 solid rocket boosters, a Centaur second stage, and a Boeing Star 48 third stage, 3 different propulsions to the spacecraft. Our little spacecraft, look at that, it's like a hood ornament on a car, sitting here. It's about the size of a grand piano, okay, about 7 feet across, weighs about 1,000 pounds. But this launch vehicle gives you several million pounds of thrust, and that's what you need in order to have enough energy to propel a spacecraft all the way out to Pluto in a reasonable amount of time. So I always like to show this. This is launch day. 2 p.m.
We have a mission.
Kennedy
and
Space
liftoff
Center.
of NASA's New Horizons spacecraft on a decade voyage
We had
to
clouds,
visit planet Pluto.
enough of a break in the clouds took off. We were over the Indian Ocean in 40 minutes.
Everything continues to look good as the Atlas V vehicle climbs.
This was 2 p.m. By 11 p.m.
The 5 solid rocket strapped
9
to
hours
boosters
later,
just fine.
we had crossed the orbit of the moon, the Earth's moon. It took the Apollo astronauts 3 days to get there. So I went out on my balcony that night. It was a nice, beautiful full moon, and I could see the spacecraft at 11 p.m. It already passed that distance. Okay? But we not only, of course, we were just headed on the beeline towards Pluto, but fortunately, and because we launched in 2006, and only because of that, it turns out that Jupiter was right along the way. And so we can use a gravity assist. We can steal a little momentum from Jupiter and we increased the speed of the spacecraft by 20% and cut 3 years off the travel time. That was the main objective of flying by Jupiter and also of that portion of the mission was to fly by a little keyhole in space that allowed us to steal that momentum from Jupiter, increase the speed of the spacecraft, and cut 3 to 5 years off, depending on exactly when we launched. So that was why it was so important that we launched in 2006. If you think about it, I mean, we were just approved in 2002. Just 4 years later, we took off and we're headed out. So that was 13 months. It only took 13 months to get to Jupiter. Okay, it took the Galileo spacecraft, which was doing the last spacecraft, which was studying the Jupiter system in detail, took 5 years. Okay, so 13 months. And I like this graph because it shows in color-coded where all the major planets are in the solar system every year. And this is the trajectory of the New Horizons spacecraft right here. Okay, and you see that in 2007, it was in late February, early March, we passed the orbit of Jupiter. In 2008, we passed the orbit of Saturn, but Saturn was way over here. You see, just look at the colors. Okay. And 2011, we passed the orbit of Uranus, and then it took us until 2014 to pass the orbit of Neptune. And then, July the 14th of this summer, 2015, after a 9.5-year journey, the spacecraft passed just 7,800 miles above the surface of Pluto. Okay? That's over a 3 billion year distance. We hit the aim point to within a few hundred kilometers. and we hit the time to within 70 seconds for over 9.5-year period. Okay, we had an almost perfect launch. It almost got us there. We had some trajectory force maneuvers along the way to get us to go exactly where we wanted, and that's what we ended up doing. Now, just as a matter of background, I just wanted to show you in a little bit more detail. This is the spacecraft. Like I said, it's about just under 6.8 feet across. So not that big compared to the Cassini mission now, going around Saturn, this huge monster. But we have these very sophisticated, advanced scientific instruments, 7 of them. Okay, we have a beautiful imaging system, a telescope called LORRI, the Long Range Reconnaissance Imager. These are our eagle eyes. This was built at APL. It's a 20 centimeter, 8-inch telescope. It's like the 8-inch telescope that some of you may have used, Ritchie Kratian telescope design. It's one of the larger space telescopes that's been put into space, but that's still a relatively small telescope. But we needed that in order to do the reconnaissance, high resolution reconnaissance of Pluto. We have this instrument called Ralph over here, which is actually comprised of 2 different instruments, a color camera plus an infrared spectral imager. We have another instrument called Alice, which is an ultraviolet spectrograph. So it's analyzing ultraviolet light from Pluto's atmosphere. And then we had 2 instruments that measure the charged particle environment around Pluto. That was another objective of the mission. The big dish here, that's the single biggest structure on the spacecraft, which, like I said, is about 7 feet across, just under 7 feet, forms the heart of the radio experiment on the New Horizons mission. And that's also critical, as you'll see later, for the probing of Pluto's atmosphere. But then we also had, for the very first time on a NASA mission, a student-designed and student-built instrument called the Venetia Burney. This is the Venetia Burney dust experiment. It's called the dust experiment. It counts dust particles. These are 12 little polyvinyl chloride panels. These are students from the University of Colorado in Boulder. I thought that was a party student. They did great. They were the first instrument to be delivered to the spacecraft, actually. And it did great science because this is the first time we're actually able to count dust particles beyond Saturn's orbit is with this mission. And these students, they've already gotten a couple of PhDs out of this, as well as lots of great results. So that's the student dust counter, the Venetia Burney student dust counter. Now, the only other point that I want to make here, though, and this is enabling for this mission, was look down here. All together, you turn all of those instruments on, draws less than 30 watts. So for less than the power output of a light bulb, you can run all of our instruments, and they weigh all together less than 70 pounds. In fact, putting all of those instruments together, they weigh less than just the single imager on the Cassini mission. But we needed that because we had to have something that was incredibly energy efficient and also low mass in order to be able to get to Pluto in 9.5 years. Okay, so just to remind you, another interesting thing about the Pluto system, when this mission was approved, there was only 2 objects. That was Pluto and Charon. Pluto was discovered in 1930, Charon was discovered in 1978. Okay? But after the Pluto mission was accepted by NASA and we're moving forward, we decided, well, we should really look more carefully and harder and find out if there's anything else in the Pluto system so we're not surprised when the New Horizons spacecraft flies by, and also so we can study them. So we met up with Hubble Space Telescope, the best and baddest observatory available to us, and in 2005 we discovered 2 new satellites of Pluto, Nix and Hydra. In fact, the first initials for Nix and Hydra is named after, New Horizons, N and H. We have to name the moons after underworld characters in general from mythology, but we picked N and H because this whole thing was motivated by the New Horizons mission. And then in 2011, we discovered Kerberos, and in 2012, we discovered Styx, which is in here. Okay, so Pluto is like a little mini solar system. So for the same price, we get to observe 6 different objects. The largest objects in the Kuiper Belt, plus small ones as well. So that was a real bonus to the mission. we have lots of scientific objectives that were put together by, over years. These missions, by the way, take decades to design, to plan. First, you have to build the case for them, make sure that the scientific community is behind the objectives of the mission, and then you go to NASA and you propose the mission, and finally it was accepted. But there was a whole laundry list of scientific objectives, but really it boils down to the three most important objectives are listed here. One is just what do these objects look like up close and personal? If you can fly by and look at them carefully, what do they look like? That's the just the basic imaging objective. The other thing is we want to know what they're made of. What are their surfaces made of? So we want to map the composition of their surfaces. And then Pluto does have an atmosphere. Coincidentally, it's actually made mostly of molecular nitrogen, just like our atmosphere here. Okay, we have about 80% of our atmosphere is molecular nitrogen. About 95% of Pluto's atmosphere is molecular nitrogen. But it's about 100,000 times less dense than the Earth's atmosphere, but it is the same molecular constituent. Okay, so now let me just get into some of the exciting results. Okay, so this is really exciting for decades. This is the best observatory available from Earth, the Hubble Space Telescope, and really this is a remarkable accomplishment when you think that this is an object that's really small, but it's about 3/4 the size of the Earth's moon, but it's 3 billion miles away. We spent decades trying to squeeze as much as we possibly could. At least it's what we call resolved. You can see at least several pixels, but it's a pixelated blob. Okay? This is what we turned it into with the New Horizons mission. This is true color. This is what your eye would see to the best of our ability to put it together. This is an iconic view showing the heart, the so-called heart of Pluto, has become so famous now. This is a giant sheet of a weird ice made of molecular nitrogen, methane, and carbon monoxide. A giant sheet of ice. It flows like a glacier too, so I'll show you in a few minutes. Unbelievable, we changed this pixelated blob into a real world with complexity and diversity. That's the reason, this is the lesson from 50 years of space missions. It turns out, on July the 14th, when we flew above the surface of Pluto, it was 50 years to the day that the Mariner spacecraft made the first planetary flyby of Mars. Okay, that was just a coincidence. But this is what we've learned, that really, if you want to really make that quantum leap in your understanding of an object, you have to go there. So that's why you have to do this mission. But just, incredible, sighting at this really bright region here that's reflecting about 70% of the light incident on it, but then you have this really dark region over here. What the heck is going on? Well, we'll talk a little bit about that. Now, instead of seeing it in natural color, though, a lot of times we take the color images that we have and stretch them a little differently in order to bring out compositional differences. This is not a cheat or anything. It's really just to be able to, and you can actually bring out, the composition of objects by doing this. And you can see in the case of Pluto, you get this, the left and right ventricles become slightly different colors. You have this, and you just have this incredible diversity of colors and brightnesses over the face of Pluto. And we can make a little movie of Pluto's. Pluto rotates. It takes 3.4 days to rotate. So we see, oh really, and we're flying by at 30,000 miles per hour. So we only get to see one face of Pluto in the highest resolution. 3.4 days earlier, we got the other side, but we're much farther away, so we have much lower resolution, and that's why it looks like there's so much higher resolution and half of the planet compared to the other. But now, we produce these, this is a map, making a map, just like you see the maps made from the Earth. This is, you've got the latitude on this axis and the longitude on this axis. We've actually put this map out on the web. You really can't appreciate how much detail is there until you download one of these, and I highly recommend that you do that, and just blow it up, magnify it, and roam around. You'll just be astounded at the incredible diversity of terrains on Pluto and the different brightnesses. We've actually started naming informally the different regions of Pluto. The most conspicuous thing on Pluto, that heart-shaped region we call Tombaugh Regio, Tombaugh region, named after the discoverer of Pluto. And it was really nice because his whole family, his daughter, his son, and some other relatives actually came to APL for the encounter and participated in it with us. And Clyde Tombaugh's ashes, we actually have some of his ashes on the spacecraft, so Clyde got to see it close up as we flew by. So, that region, that big giant sheet of ice is called Sputnik Planum. We're naming the regions after, the various spacecraft. You're starting out in the lower left-hand corner. These are real spacecraft images, but just put together in a movie, so you can pretend like, it can seem like you're flying over Sputnik Planum. Let's just run that. So we're starting down there. We got mountain ranges, okay, down there. We're coming up around Sputnik Planum, and this is a region called chaotic. We call it chaos. Up here, you have the glacier flow that I'll show you, show you in more detail in just a minute. But this is just one of the people on our team put this together. These are like I say, these aren't artist renditions. This is the actual images put together in movie form, so that you can see, just get a sense. Now, so here, I'm going to pick out 6 different regions and then blow them up for you. Because like I say, in order to appreciate, to think that we went from that pixelated blob to this, that was called planetary astronomy, to really planetary geology with this. Just to show you some of the diversity of the terrains, let's just walk through some of these different regions, okay? But this is before I do that, I'm going to step through each of these, and so you can see where they are in that big picture. This is that northern edge of Sputnik Planum, and you see the little swirly areas here? That really screams out at you that you have ice flowing around barriers, and in fact you have it breaching the uplands, the highlands over here, okay? And we have really good evidence now that it really is like glacier flow on the Earth. This is molecular nitrogen, which is a very soft substance that's almost playing the role of like water ice on the Earth. Don't forget, at Pluto, the temperature of the surface is like minus 390 degrees Fahrenheit. Okay, I know that when the temperature is that cold, water icing is more like a rock than the ice that you have in your refrigerator. But molecular nitrogen is an extremely volatile molecule. You have to get down to temperatures about minus 390, and then it's more like water ice at 32 Fahrenheit. Okay, but we see flow of that nitrogen ice. Here's another example where instead of flowing out of Sputnik Planum, we think that some of that icy material actually is sublimed to go straight from the solid phase into the vapor phase, goes over to the eastern part, coats that higher region, then becomes icy, and then actually flows back into Sputnik Planum. Across, and that's what's happening in these channels. You have this pitted region that had partially filled in with ice, but that ice then runs downhill into Sputnik Planum. This is one view at high sun illumination, so the sun is almost like noontime. But when you look at it from the side, you get a very different view, but you can see the flow regions better. These are a couple of miles across. These channels cut through Pluto, where the ice is making its way back from the highlands back down into the Sputnik Planum region. Mountains. These are giant ice mountains on Pluto. We think that this is Norgay Montes and Hillary Montes. These are the explorers of Mount Everest, of course. The Sherpa, Norgay, and Hillary, Sir Edmund Hillary. The Norgay Montes are about as high as the Rocky Mountains of the United States. These are giant chunks of water ice. It can't be molecular nitrogen ice because that's too soft and porous, okay? We think that this is protruding. We think underneath that nitrogen ice is basically a crust of, the base is water ice, but it's more, like I say, more like rock. But you have these huge regions where it's kind of just sticking out, jutting out like giant icebergs. And that's what these mountain ranges are. So this is that region I was calling chaos before. Look at this, and this is gives you the scale, 50 miles across. There's an upturning and downwelling of material. These giant ice boulders are being lifted up to the surface and moved around and creating this chaotic environment. This looks very much like what we see on Jupiter's moon Europa, a region that's been called chaos there, and it's because of, basically ice melting and freezing and breaking up and, creating chaos, what looks like a chaotic region on the surface, and it's happening even on a bigger scale. These are even larger spatial extents in Pluto's case. Look at this. I mean, these are things, by the way, we just started downloading these images, Labor Day weekend, okay? And every day, we just get these things coming down. So, and it turns out most of these first images have been coming down over the weekends. The science team, our jaws have just been dropping as these data are coming in. I mean, when we see something like this, we had no idea what to expect. I mean, we've never been into this region of the solar system. And look at this, we're calling this snakeskin. There's always these aligned features. You get these ridges, but these aligned features, we're not sure what's going on there. You have cooled ice over here, plus all of these alignments. Uh-oh. Now, this is one of our highest resolution images taken in the middle of that Sputnik-Planum region, and there were all these geometrical structures. If you look out on a lake, a frozen lake, sometimes you see these geometrical structures, and that's what we're seeing on Pluto's surface as well. But you have a couple of isolated ice mountains in the middle of this icy plains. But look at this. Just a couple of weekends ago, I had this come across my screen. And so this is a sunset on Pluto. We've already flown by. We've gone by only about 5 minutes after closest approach. Now we're looking back at Pluto. So the sun is into the page here. Okay? And we see this incredible panoramic view of Pluto, but this stuff, that's not noise, that's haze. You can actually see Pluto's atmosphere. This is haze in Pluto's atmosphere. And I blow it up a little bit. This is Sputnik-Planum here, and it looks different. This is very low angle, right? The sun is just, over the horizon. Look at this, I felt like I was there. Just these, here are the Hillary Montes. You see the shadows cast by the mountains, and just incredible detail. To think that we had this little spacecraft, traveling 3 billion miles and producing these kinds of images, everything just worked beautifully. It's been really rewarding. Okay, so that's Pluto. Just phenomenal diversity of terrain. This is Charon, the large moon. Now, this is really a binary planet system. Charon is about half the size of Pluto. The center of mass of the system is actually outside of Pluto's physical body, in between the two. This is not seen anywhere else in the solar system. So they're both rotating like a dumbbell around their common center of mass. Okay. So that's it's outside of Pluto. The center of mass of the Earth-Moon system is well inside the surface of the Earth. But that's not the case here. It's really like a binary planet system. So you call Charon a moon of Pluto, but it's more like a cousin. Okay, so but Charon, this is a little movie showing you some of the actual images. Oops, sorry. There was this big dark spot around the pole, the North Pole. That's the North Pole of that dark region. That was a mystery to us. We did not know about it. It looks like this is it's not going very smoothly here. But this is a flyover using actual images. The main features that we see on Charon are this hood of dark material, which we're thinking might be, because that dark material looks kind of like that dark material we saw along Pluto's equator, we're thinking we're actually transferring material from Pluto to Charon, and in regions that are especially cold where that material can condense and then be irradiated over geological time, form the dark hood, just like what happened on Pluto is happening on Charon as well here. But we have this, it looks, let's actually look at This is just a map of Sharon. I'm not going to stick there. Look at Sharon. Look at this. This is enhanced color, but it has a giant gash through across its equator. Okay? This is the North Pole, that dark region. It looks almost like it's been split. It has this huge, and this is like a canyon, but it's much bigger than the Grand Canyon of the United States. It goes 1,000 miles across and, all the way around and much deeper. Several, a couple of miles deep. And when you look at it even in more detail, we have a mountain in a moat here. That little region right there, you blow that up and look at it at even higher resolution, you have something like this. Now, they really are two different worlds, Pluto and Charon. We've taken those two images, we've stretched the colors in exactly the same way, there's no cheating here, and their brightnesses should be directly comparable. We haven't tried to boost one relative to the other. This is the way they were observed, and you can see the clear differences between the two. Charon is darker, about half as bright as Pluto. Okay, it's much grayer. Pluto has a lot more color and a lot more brightness variation. Okay, so they're two very different worlds. Okay, now in addition to just doing remarkable resolution on Pluto and Charon, we also can finally see those tiny moons resolved for the very first time. We can actually see how big they are. With the Hubble observations, all we saw was these little pink points of light. We had no idea what the reflectivity of the objects were, so we didn't know how big they were. But with new horizons, we can actually directly measure their sizes. And this is Nix, what it looks like, and it's a highly elongated body. At one orientation, it looks like it's almost circular. Then you rotate it, it becomes almost 2 to 1. And then this is on this one is at the after we've flown by. We actually have some color data. It looks like there's a giant crater in the center of Nix, and it's a different color than the rest of the objects. And so that will be of great interest for us to investigate. Hydra, which is just a little bit bigger than Nix, they're approximately the same size. It looks like it has a couple of chunks taken out of it. Okay, a notch here, right here, or maybe a crater here, another notch taken out here. It looks almost a little bit like Churyumov-Gerasimenko, a two-lobed object. You get the head and the rest of the body. Styx, we just got down on Monday of this week, is even smaller. It's a tiny little thing. It's probably only in the long distance, and it's also highly elongated. It's probably only about 5 kilometers, so, about 3 miles across, maybe 3.4 miles in one direction and a couple miles in the other direction. And this is just a little orbital diagram to orient you. Again, Styx is the one that's closest to Pluto and Charon, and then you get Nix, and then Kerberos, and then Hydra. Okay, let me just quickly show you some of the composition results, because we were trying to map the composition of the surface, but it turns out that that's a lot of data to send down, and we haven't gotten very much of it down yet. We've only got half the face of Pluto here, but we've colorized it so that the pink is showing you where there's strong methane absorption. So methane ice is prevalent in the regions that are pink, and the dark region is where there's hardly any methane. That very dark region near the equator, and that's near the equator of Pluto, that region that looked blackish, this has a reflectivity of only about 10%. It seems like maybe that was once covered with methane ice, but has been irradiated, and the molecules, the bonds have been broken and reformed into these complex hydrocarbons. We think that's what's happening. We have a generic term for these types of complex hydrocarbons called tholins. We first were thinking about them in terms of Saturn's moon Titan. You see evidence that these materials exist there. And they have spectra which are similar to what we observe from these objects, Titan and now here Pluto. Today, we just announced the discovery of water ice. I told you that there's a lot of water, there's water mountains, there's water ice underneath, we think the molecular nitrogen, but the problem is you can't see it directly from Earth because you don't have the resolution, the spatial resolution, because even though you have a lot of water ice around, the methane absorption is so strong that it washes out the signature of the water ice. So you can't, it may be there, but you can't see it until you get the spatial resolution, and some places pop out in blue here. Places pop out where we see clear signatures, spectral signatures, compositional signatures of water ice. Okay? And this is the first time this has ever been accomplished. We're not sure why we're seeing it here and not in other places, and but that's what we're going to be working on. Now, let me just quickly tell you about the atmospheric results. Because we had this really neat experiment. This shows the trajectory of the spacecraft. That red line here is the spacecraft trajectory through the Pluto system. And I didn't mention this before, but Pluto, in addition to having this weird orbit around the sun, is also tilted over. The whole plane, it looks like a bullseye, but it's tilted with respect to our view from the Earth and from the spacecraft. So we flew through like this, that the sun is way over here to the right. We actually, one of the mission designs was to fly through the shadow of Pluto, right through the middle of it. That was what we tried to do, and it turns out we hit it right on the button. Oops. So, and the reason for that, we had two experiments. Okay, one was to use the deep space antennas on the Earth, and from NASA's Deep Space Network. These are giant 70-meter, over 200-foot wide antennas, single dishes. There's one in Canberra, Australia. There's one in Goldstone, California, just outside of Los Angeles, and there's another one just outside of Madrid, Spain. Those are beaming up 85 kilowatts of power up to our spacecraft. So as the spacecraft passes behind, here's the light there. As the spacecraft passes into the shadow, our radio receiver is locked onto those radio waves and watches the change in the phase of those radio waves as they're bent by Pluto's atmosphere. And it turns out they're bent depending on what the temperature and the mass, mean molecular mass of the atmosphere is, okay? The amount of bending. So we can actually derive from these measurements the atmospheric pressure at the surface. And that's never been done before, and that was a result we already have from the New Horizons spacecraft. That was one experiment. The other experiment, because if you think about it, so the spacecraft is about 32 AU from the sun. Now you're looking back at the Earth and the sun, they're only a few degrees apart on the sky. They're almost next to each other. So at the same time, the radio antenna is looking at the Earth, our ultraviolet spectrograph is looking at the sun. Okay? It's using the sun as a candle, basically, as a source of light, and we look at absorption by molecules and atoms in Pluto's upper atmosphere with that ultraviolet spectrograph. All molecules and atoms have characteristic fingerprints, absorptions, that tell you what the composition is. And we use that to gauge the composition of Pluto's upper atmosphere. And this just shows you schematically, well, this is real data. What happened as we were out here, before we go into the shadow, we go into shadow, and you see there's not a sharp bend. It's not a sharp drop-off. It's skewed a little bit here. You see it's sort of just gradually going down, down, down. That's because there's an atmosphere there. If you compare that to Sharon, look at that. Okay, when we flew by Sharon, it was much sharper because Sharon doesn't have an atmosphere that we've been able to detect yet. Okay. From these data, we can put even tighter limits on how much of an atmosphere Sharon might have. Now, this came out today. Okay, a new release. After we've flown by Pluto, this is a true color image. It's a blue haze. Pluto has a blue sky, just like the Earth does. This is amazing. So this is, so what you're looking at is a little crescent of light. It's you see a little tiny crescent being directly illuminated, but you see fuzz all the way around. That's because there's this haze layer of material around Pluto, its atmosphere, in clouds, and they're actually structured clouds. Okay, now finishing up the New Horizons portion of the talk. This mission is not over, but we've been continuing to fly at over 30,000 miles per hour away. We're already 7/10 of an AU from Pluto. So the same distance from the Sun to Venus is how far we're away from Pluto now. But we're going deeper into the Kuiper Belt. We've already identified a target that we can fly by. We reach it on January the 1st, 2019. If we're approved by NASA to do what we call an extended mission, in the next couple of weeks, we're actually going to fire we have a little bit of fuel that we can use to move the trajectory of the spacecraft to head it towards this object right here. It's called 2014 MU-69. It's one of those, the third category of Kuiper Belt object that's formed almost probably in place and doesn't have very much of an inclination to the rest of the, to the ecliptic plane. Maybe the most pristine material out there, okay? We have identified an object, we hope to fly by it, we're going to make the maneuver to enable that to happen, but we have to write a proposal to NASA next spring to make the scientific case to, to get the funding to do that. But we're hoping the spacecraft is still working great, everything is working beautifully, there's no reason not to do this, and we feel pretty confident it'll happen, but that's where we stand right now. So, but let me just mention that really the results are continuing to pour in. I really encourage you to go to our website, pluto.jhuapl.edu, to check out the new results. Okay, now let's move on to the other mission, which is looking at a Kuiper Belt object. This is one of those scattered disk objects that's now in the inner solar system, Churyumov-Gerasimenko. This is a completely different mission. I didn't mention it, but the New Horizons mission is nuclear powered. Okay, by the time you get out to the sun, to Pluto's distance, the sunlight is 1,000 times fainter. You can't build solar panels big enough to give you enough power. Okay, we had to use the spares from the Cassini mission from the radioisotope thermoelectric generator. This is plutonium-238. It's actually highly radioactive, physically hot. That's providing our power. At the launch, we had about 240 watts of power. At the time we get but it's decaying over time. It has about a 7-year half-life. By the time we get to Pluto, we ended up with about 200 watts. So we had 200. We needed at least 160. We had plenty of margin to do the mission. But at 200 watts is what we used. In contrast to that, the Rosetta spacecraft has these huge, 32 meters across, solar panels. This was an incredibly ambitious mission. It not only consisted of, there's the panels, the real panels, and you can see the scale, see the size of the people there. These are just huge things. Let me just mention, of course, the objective of this mission was, these things. I won't read each of these to you, but I mean, it's really to, we think that these are relatively pristine objects that nature has given us a gift. We moved it from the Kuiper Belt into a region of the solar system that we can actually more easily reach it. Okay. Although it's funny, this mission, first of all, it consisted of an orbiter portion of the spacecraft, which has 11 instruments on it. But then it had this little, you see this little thing right here, down here at the bottom. That's the Philae lander. That's the portion of the spacecraft that's going to be ejected and landing on the surface of the comet. Okay, but look at this. It's a very complicated thing. You have to stare at this for many minutes to understand it, but the center of right here is the sun, okay? It's 0, 0, okay? The Earth's orbit is, and these are in units of AU, so the Earth is just a circle around here. So this mission was actually launched in March of 2004, a couple of years before the New Horizons mission, but it arrived at its target only 1 year before us, so it even had a longer time frame, but it was just doing a dance in the inner solar system. The orbit of the comet itself is this red thing, okay? It goes up beyond Saturn's orbit and it comes back in. And it had its closest approach to the sun just this summer, in August, okay? And that's why there's been so much excitement, because we picked up the comet, we rendezvoused with it back in May, and then in November of 2014, when it was here, this is where the spacecraft met up with the comet right here. That's when we tried to drop off the package to land on the surface, okay? But then we continue to follow it. We're just in orbit around the comet and just following the path around the sun until we pass through perihelion, and now we're on this side, and that mission is continuing to go on. It's still producing fantastic results. It had 10 years of cruise. It actually flew by the Earth a couple of times. It flew by Mars. And it flew by 2 different asteroids, Steins and Lutetia. I don't have time to go into these things. But this is just the thing that I'll emphasize here is the drop-off of the lander, because that was kind of a cool story. It didn't work out completely well, unfortunately. But we'll hear about that in just a second. So this was the plan, was to drop off this lander onto the surface. And this is what it looked like so we're taking images of this thing, and the poor team that had to worry about landing on this thing, the thing is rotating at about 12 hours, 12 and a half hour period. It looked like a rubber ducky. That's what it was called. There was lots of, it had the head, a neck, and a body, and it looked really, really complicated. This is a selfie taken by the camera on the Philae lander, showing you the solar panels, and there's the comet from 50 kilometers away. Okay? So this is the problem. You have to land somewhere on this thing. Where would you pick to land on this thing? I mean, it really was a big problem. Basically, what you try to do is you find a place that looks the flattest, because you have some uncertainty in how well you can navigate and put the thing on the surface, and so you have to take all of that into account. The comet's spewing stuff into space as well, so you have to worry about not going over a vent, a jet. So the team identified about a handful of potential landing sites. This is all happening in the summer of 2014. Okay, so a year ago, a little over a year ago, they were trying to figure out, they were looking very carefully, they created what were called digital terrain models of that very complicated object, trying to identify places where we could land. Okay, and so these are actual pictures taken by the OSIRIS scientific camera on the spacecraft of the lander package as it's heading down to the surface. Okay, isn't that cool? I mean, it looks like a little Pac-Man or something. And these are real images taken of the space. So it's taken by, you're off and going to land. This is the trajectory they're following. They just put together this little thing. So this is where we tried to land, right there. Okay, if you look at it closely, there's a big boulder over here, but it looks relatively flat there. But this is what happened. Okay, this is actually taken by the orbiter, the high resolution camera on the orbiter, looking at this place. Look at it, and these are the times: 15, 14, 15, 19, 15, 23. You can see the spacecraft right there, and then blown up right there. They're following it as it flies over the surface of the comet, and then it touched down. Everybody said, "Yay!" In the control room, it touched down. But unfortunately, it bounced. It bounced off, and it moved almost a kilometer. And the reason it bounced off was because originally what they were going to do was fire some thrusters as it was landing. They were supposed to fire some thrusters that was going to push it down into the ground, and they had these harpoons that were supposed to fire and anchor them. Neither of those things worked, unfortunately. So comet nucleus it's almost 75% is porous. It's vacuum. This very porous object has very little mass. When you land on this thing, you bounce off, you can actually be ejected into space at that point. It doesn't take very much. I mean, you can almost bounce, if you were on that surface of that object, you'd almost jump off and leave it. And that's exactly what happened. The thing, it landed, and then it actually went almost a kilometer, hit again, bounced up again, and then we think it hit a wall, a cliff, and finally ended up. These are. I don't really have time. This is the little footprint. We can tell. We put together do the forensics of exactly what happened. I mean, the poor people who it didn't work out quite the way we had hoped, and we're doing all the forensics about exactly where it was by looking at these high resolution images. But here's where we ended up. This is the camera, and it's just right up against the wall. I mean, it's just, and it's also partly cocked. So a lot of, so there's a couple of huge problems associated with that. It was running off of batteries, okay, solar power batteries. And so it had a couple of hours of battery life, and they get data from that, but they were hoping originally that they would have been in sunlight for most of the time, as the comet rotates, and they would be recharged, and so they'd have a couple of weeks of operation. But unfortunately, it's now sitting next to this cliff, being shadowed almost the entire time. And so once the batteries ran out, it was dead. And that's what happened. You know, this is our best estimate of where it finally ended up. They did have, you know, first of all, we got some great results anyway from just the time that the battery was operational. And we get, you know, these results, and on the cover of Science, and this is their best artist, you know, view of where it finally ended up. This is the result from one of the mass spectrometers. Look at all the different species that were detected, very complex species. Comets are loaded with water. People look for years for water on Mars, but I mean, comets are chock full of both water and organic material. Okay, complex hydrocarbons. We think amino acids. These could be basically seeding the solar system because they come in from the Kuiper Belt and they get passed through the inner solar system, seeding everywhere with the building blocks of life. But, you know, for a long time, a lot of us have thought that comets were probably a major contributor to the water on the Earth, okay, the oceans on the Earth. But so how can you tell? Well, a couple of ways. One, a very important way to tell is to look at the ratio of heavy water to regular water, an isotopic form of water to regular water, and using that as a probe, because that's something that's sort of characteristic of material that doesn't change with you know, just the amount that you have, right? It's a signature. And it turns out that the level of deuterium to hydrogen, heavy water to light water, is this horizontal blue line here. Okay, there's the Earth. Comet Churyumov-Gerasimenko has a number way up here. Okay, about 3 times higher. So a comet like Churyumov-Gerasimenko could not be a very significant contributor to the water inventory on the Earth. These other measurements here are of all the other comets that we've had measurements like this done remotely. We didn't have as much power as what we had on Rosetta. But there is one comet, 103P Hartley 2, which was, if you remember, the Deep Impact spacecraft, which launched a projectile at Comet 9P Temple, but then after that, a couple of years later, it flew by Comet Hartley 2 and measured the DDH ratio. Actually, that experiment didn't measure the DDH ratio. It was the Herschel space telescope, infrared space telescope, that measured the Hartley 2 DDH from the spacecraft observatory and got a number that was right on. So the jury is still out as to how much comets can contribute. Most of the comets we've observed so far could not be significant contributors, but maybe, depending on what the flux of comets was through the inner solar system. You could explain all of the water just as being from the water that's in water-bearing minerals in the asteroids, okay, that are in the asteroid belt. The things that would, because there are, we're raining down with meteoritic material from the asteroid belt onto the Earth, and that may be where most of the water comes, those what we call the chondrites, because they land right in the right region. So with that, I don't even want to get into this, it's a little too complicated. Just to show you some, when the comet, when we got near perihelion, more and more activity is just these, this is just an outburst, just a few seconds apart, you take these images, look at that, very, collimated thing, just fantastic results. I mean, here's a picture of the comet. We've now identified all these different regions on the surface. You see these beautiful dust jets. We're starting to do the science of, okay, well, what's driving the activity on these comets? How is it being produced? What is the molecular composition in detail, and so forth and so on. All of that's happening. So, go to the ESA website. NASA at JPL also has a Rosetta website because the United States contributed pretty heavily to the Rosetta mission. We have, we have 5 instruments, including the one that I work on, the ultraviolet spectrograph. So we've made a significant contribution to that mission. It's ESA-led, European Space Agency. It's a very ambitious mission. They're doing fantastic stuff, and it's still doing some fantastic stuff. So I highly encourage everybody, go to the Rosetta website and the New Horizons website, because there's still lots more to be done. Okay, thank you very much.
thanks a lot to Dr. Hal Weaver of the Johns Hopkins University Applied Physics Lab for giving us a little tour of the third zone of the solar system. These are two objects. There are a few more to explore, which may take a while. In the meantime, we have time for a few questions, and I want to make some announcements.
Yeah, let me just say, I mean, you can't just rely on space missions. They give you ground truth on a couple of objects, but you also like to have continuing ground-based measurements that then you can tie together with the ground truths from the space missions and really put together a more complete picture. So, for example, we'll continue to study cometary nuclei, and we do that, for example, a program I'm involved with, the Apache Point Observatory in New Mexico. We observe cometary nuclei because we can see them, the light reflected from the nucleus before they form the coma, and we can measure sizes and shapes. Then you can address them as a population, right, as opposed to single objects. Because right now, if you only have a handful of objects, it's hard to know how general the conclusion you can draw. So you have to have the ongoing ground-based program, like the things that we have on the observatories on the Earth, in order to support the continuing, knowledge.
Could you tell us just a little bit about the Apache Point Observatory and how Johns Hopkins relates to it?
Yeah, so this is out in New Mexico, and it's a there are a couple of the Apache Point Observatory is about a 3-meter telescope, in the mountains there. Hopkins bought some time. There's a consortium of universities that run the observatory. In addition to the 3-meter telescope, there's a 2.5-meter telescope that surveyed the entire northern hemisphere sky. It's called the Sloan Digital Sky Survey. A lot of good work going on, and this consortium of universities run both of those telescopes, and they've done fantastic jobs. But you have to, we have like an 8% share. Hopkins does in that telescope observatory, and it's really great, especially for training students as well. They can actually, you can do remote observing, but you have to go out there and get trained first, but then you come back to your home and sit in your computer in your room and observe the universe. It's really cool.
Have any students here used the Apache Point Observatory? Yes. How was it?
Oh, it was amazing. It was the best experience I've ever had observing. It's gorgeous out there. And you can get really good data off their instruments as well.
All right. We'll open up the floor for some questions, but we'll also have a session with Dr. Weaver outside. So we'll take a few questions here, and then you can talk to him up close and personal afterwards. So open up the floor. Please speak loudly.
Yeah.
As the main here is the origin of the water,
Uh-huh.
one or the other?
That's pretty much the main one. That's we think is most diagnostic. Yeah. I mean, the other things are oxygen isotopes and the nitrogen isotopes, for example. Those are other things, and then and then noble gas abundances. Those are other things, but the one that's been, we think, is most diagnostic so far has been the head and water.
Yes.
Mission, an actual landing of the probe?
Yeah.
Is that in the works?
You mean to an object in the Kuiper Belt? Or Pluto? Yeah. No, I mean, we'd love to. In fact, a lot of people say, well, did you go into orbit around Pluto? Well, we flew by it at 30,000 miles an hour. And we had to do that in order to get there in a reasonable length of time. If you think about it, if you want to go into orbit around, see, Pluto is so small, it's not a giant planet that you can use its gravity to capture it. And it would take you almost as long to slow down as to get there. So really, it'd be like double the length of time. And there's no missions on the books right now. This really was a once-in-a-lifetime opportunity, and that's one of the reasons why we're so anxious to not let it die at Pluto, but to fly by another Kuiper Belt object, because it ain't going to happen again for at least, I would say, 30 to 50 years. Yeah.
More questions? Wait, let me get the mic up to you.
What is the relationship between the Kuiper Belt and the Oort cloud?
Yeah.
You pronounce that properly.
Oort cloud, yes. The Dutch have dominated the outer solar system. Jan Oort was in fact, he proposed the existence of the Oort cloud around the same time. This is 1950 was a great year. And that's the time that Fred Whipple had his model for comet nucleus first published as well. But Oort when you saw that diagram with those little caret symbols with all the comets, you saw the ones that were really coming in from weird angles, the high inclinations. Those are coming from the Oort cloud, we think. So they are in million-year orbits or longer. We think that those objects originally formed in the giant planet region, 4.6 billion years ago. But as those giant planets form, the gravitational interactions with the remaining planetesimals tossed a lot of them out of the solar system, but some of them it ejected to the just being barely held on in the solar system, and more or less formed a disc-shaped object much farther out. But that eventually got isotropized by passage through galactic tides and also nearby passing stars, forming this roughly spherical cloud extending from about 10,000 AU to about 100,000 AU, which is about halfway to the nearest star. That region, those objects are still gravitationally bound to the sun, and they're the ones that, depending on when you have a nearby passing star or a perturbation from, just the tide in our galaxy, can perturb the orbit so that it now, it basically falls towards the sun, and those become the long period, what we call the new comets, that are coming in for one time only. They come in, and that's like Hale-Bopp and some other comets like that. They come in. We think that there's like 1 trillion objects out there, and that's probably, it's been depleted over time, but it was maybe even 10 times more in the past at the early formation of the solar system. But they ultimately came from much closer in. In fact, the funny thing is that most of them, we think, on average, came from a region originally closer to the sun than the short period comets, which are coming from the Kuiper belt, the classical Kuiper belt. So you have the Kuiper belt, which extends from about 30 AU to about 50 AU. You go out a little bit further, and there's something called the inner Oort cloud, and that goes up from about 50 to 100 AU. But then you have the traditional Oort cloud, which is about 10,000 to 100,000. And all of this we've just put together in the last 50 years of the 20th century.
Just for scale, 1 light year is roughly 70,000 astronomical units. So we're talking about a light year.
Yeah.
That's a fair distance. It's a chunk of the way to the next star.
Yep.
So that's some part of it. More questions? Yes. Speak up, please.
Thank you for inviting us. I really like the lecture, and I was wondering what hydrocarbon is.
Oh, hydrocarbon. Okay, that's something that has hydrogen and carbon. Okay, so the simplest ones are like methane, for example, as a hydrocarbon. They really they're what we consider the building blocks of life in addition to water. So water is not a hydrogen, it's H2O, but things that have carbon and hydrogen together with water is what we need to have life as we know it. So that's why we give so much emphasis to it. It's organic chemistry. And you eventually get up into sugars and amino acids, and it becomes, things that, and like I say, we've already had a situation where we know about amino acids in comets. So whether or not those are raining in and, producing, giving you the raw material for life elsewhere in the solar system, like in Europa or, the moon of Jupiter or other places in the solar system, that could be going on.
Also beside you, yes?
Thank you for having us today. I really enjoyed listening to your lecture and I learned a lot. I was wondering how long the entire thing took.
Yeah, so our mission launched in 2006, but we had to back up. I mean, we started planning this mission back in the 1990s, so roughly 10 years earlier, and then it took us 10 years to get there. So you're talking about a couple of decades for some of the people involved in our mission. Now, I first joined this mission in 2002, so I've been on it for 13 years, myself. So that's tough for some grad students, to be on there that long, but it's really exciting, and I hope that, I'm glad that you came, and I feel blessed that I have, I'm able to do this for my job, and I get paid for it. It's just so much fun. It's very intellectually stimulating. I highly encourage you to continue, following your passion in school, and maybe it'll be science and math or whatever, but really, we have a very diverse group of people working on our mission, lots of women and men, and young people. We have postdocs who are just finishing their degrees, and they came in at the right time. We just hired them in the last couple of years. They're really making out. And they can't believe it. I think, well, see, this is the problem. Life is not always like this. They're going to learn. And that's one of the sad things about this. This year has been fantastic in terms of what's been happening. What's in the future. The planetary budget for NASA has been cut by 30%. We're going into a bathtub of inability to do these kinds of things anymore. And it's really terrible because, the United States, in order to maintain our leadership internationally, I mean, we're going to, others are going to take our place, if we don't step up to the task. And if you think about it, if you ask people how much money is being spent on NASA, a lot of people say, 30% of the federal budget. It ain't that at all. It's less than 0.5% on the dollar. It's a relatively minor investment for a huge payoff in terms. We do this because we're human. We're interested in exploring and learning about our place in the universe. And a lot of times it turns out that these really benefit us practically as well. But sometimes it'll be 10 years later. And all the communication stuff that we have now, has come out of the space program. And there's so many. So much technology that's developed as a result of doing this kind of work that I think it really pays off in the long term. You just have to think long term, and sometimes that's a problem. It's not that you shouldn't try to solve other societal problems, but you can't just not completely forget about science and art and things like that. You have to do those too. And Stephen Hawking was a big proponent of the New Horizons mission. We had a wonderful video that we were showing during the Encounter Week where, the final line was, we're doing this because we're human and we want to know. That basically summarizes it. We're curious. We want to know about why we're here and what is our place in the universe, and this is the way we go about figuring it out.
The next people to send a probe to Pluto are probably about 10 years old, 10 or 12 years old, so that's you.
Yeah.
You're the next people
You'll be the next principal
to send
investigator.
to command and do principal investigation on the next probe. You're probably in 5th, 6th, 7th, 8th grade. Okay, another question.
Dr. Weaver, knowing what you know about Pluto at this point, would you promote it back to full planethood?
When the International Astronomical Union put out the new edict that Pluto is no longer a planet, I was the first person to sign the petition that said, yes, it is. Because, I don't really care too much about that because, most of us, there's a consensus that's been reached, among professionals that it's a dwarf planet, and that's fine. I mean, it's only 3/4 the size of the Earth's moon, but there's lots of planetary processes occurring on Pluto. And that's what our gripe with the International Astronomical Union, there's a bunch of astronomers, they didn't know planetary science. We're the planetary scientists, and most of us think that, my gosh, when you see all of these terrains, these different terrains indicating there's tectonics going on this object. We wanted a more geophysical-based definition of a planet. Most of us, felt that way. And so I would call it, but I don't mind calling it a dwarf planet. And, I don't want to get into that argument because ultimately Pluto is what it is. It doesn't make any difference what we call it. We try to pigeonhole things to help us understand, how to compare different objects. But ultimately, nature is just beautiful in the diversity of phenomena that it presents us with, and there's something great to be learned from these tiny objects.
I'm going to take 2 or 3 more questions. So I have 2 from future NASA investigators here.
Thank you for coming out. I was wondering how roughly how much water ice was found on Pluto?
Yeah, so it was a struggle to find that water ice, but we really think that there's a lot more than what, than what we've seen so far. But it's just being covered up by this other stuff, the methane ice mainly. Exactly how much and how much, for example, it compares to the oceans on the Earth, I haven't done the calculations, so I don't know. But there's probably a lot of water ice on Pluto, because water is a very common constituent throughout the outer solar system.
Next question.
Thank you so much for calling on me. My name's Eliza, and I go to St. Francis of Assisi here in Louisville. And I had a question. You said that there is a lot of glaciers made out of nitrogen molecules. What kind of equipment and observations let you know that that was made out of nitrogen?
Great question, yeah. You can't just believe what I say. We have to show you the evidence. Well, first of all, like I said, regular water ice is like a rock at these temperatures because it's so cold. We bring water ice, and we know this from laboratory studies, and we also know from we can make in the laboratory molecular nitrogen ice and molecular methane ice, and we can produce mixtures of them. And it's from those measurements, the thermophysical data that we collect by those laboratory measurements that allow us to figure out that, okay, what must be happening on Pluto. In addition, we have this infrared spectral imager, which can measure little dips in the spectrum of Pluto. This is the light that comes from Pluto. You break it up into its component colors, and it turns out that molecules and atoms, they have characteristic absorptions that have to do with they're really truly fingerprints of those specific species and nothing else. And we can see the signature of molecular nitrogen ice. And same thing with the methane. So, a lot of times we don't show those data to public audiences because they're squiggles on a drawing as opposed to a beautiful image. But that's the evidence, are these what we call the spectrum.
If you go to a